So boundary of a simplex, let's say simplex is sigma, is defined as linear combination of their faces. Linear combination of we have already talked about how to compute faces for a simplex. The linear combination of all the faces of a particular simplex is defined as boundary. The symbol del is used to denote boundary. So for sigma complex, so simplex sigma, this is the notation of boundary, and we also write small k in subscript to denote that this simplex is defined from vertex v0 to vk. So this denotes boundary of simplex, or I can say k simplex sigma. Vertex set is from v0 till vk, right? And how you can compute it? It is actually equal to a linear combination from I equal to 0 till k of all your faces. So 0th phase, first phase, second phase, third phase, fourth phase, fifth phase, whatever your phases you have, we compute the linear combination with alternate sign. Okay, so we start with plus sign. So 0th phase will get positive sign, then first phase will get negative sign, then second phase will get positive sign, so on. So we can also write it like this. So here k means the simplex is k simplex, okay? Or you can also say that k is the dimension of your simplex, right? K is the dimension. You can also say dimension of your simplex, okay? So this del k sigma will be equal to plus your 0th phase, right? Then minus your first phase, then plus your second phase, then minus your third phase, and so on, right? And we know that how you denote your phases. So plus of sigma minus 0, minus sigma minus 1, and then plus of sigma minus 2, and so on, okay? So let us take some example of some simplices and calculate the boundary over them. Let's say my simplex is sigma equals to v0 v1. So it's a one simplex, and you can visualize it like this: v0 v1, right? So let's compute its boundary. So boundary of since it's one dimensional simplex, so I'll write 1 here, right? So del 1 of this sigma is nothing but del 1 of what? Del 1 of this v0 v1. So plus what will the first phase? hide this v0, and whatever you get hiding this v0 will get v1 only, and v1 is just a single vertex, right? So this will be a single vertex v1 first phase. Similarly for second phase, if we delete v1, we are left with a single vertex v0. So this linear combination of faces is boundary. So boundary of this edge is the linear combination of its faces, which are linear combination of their vertices. We can also write it like this: del 1 of v0 v1 plus v1 minus v0. Let's take one more example of two simplex for the clarity. So let's calculate del. So since we are considering two simplex, so we'll write subscript 2 here, and I'll have something like this: v0 v1 v2, edge edge, and the triangle is filled. So let's compute boundary of this simplex. Boundary of this simplex will be what? Plus, and you will eliminate vertex v0, and you are left with v1 and v2 only, right? So when you eliminate v0, you are left with v1 and v2 only. So it will look like this: v1 v2, right? Then minus, eliminate this v1, we are left with this edge only, v0 v2. So it will be like this: v0 v2. Then plus, this time hide the or terminate delete the v2, we are left with v0 v1 v0 v1, right? And instead of writing this with these pictures, you can just write del 2 of v0 v1 v2 equals to v1 v2 minus v0 v2 plus v0 v1. Now what is the boundary of a zero simplex? We have talked about one simplex and two simplex. So one simplex have dimension 1, two simplex have dimensions 2. So what is the boundary of a zero simplex? So in zero simplex, we just have a vertex v0, and we cannot go down further, right? So vertex does not have any boundary. So we explicitly say that for del 0 we have value equal to 0. So whenever someone tell you that this sigma is zero simplex, what is its boundary, then you will simply report at 0. So 0 is the output for boundary of a zero simplex or one zero dimensional simplex. One more important result that we have to consider is that boundary of boundary is 0. Boundary of boundary is 0. Now what was boundary? We have already defined above that boundary is linear combination of faces. So those linear combination that we got, apply boundary operator again on that. If we apply again, then we will get 0. This is a result. This is true result, right? So boundary of boundary is 0. I will not prove it, but I will show it for a 2 simplex. Okay, and you can write it like this: boundary of k simplex over k minus simplex del k minus 1 of del k equals to 0. So since if I get boundary of k simplex, then all the faces are of dimension 1 less than that of simplex, right? So when we applied boundary operator on this simplex, which is of 2 dimension, we got linear combination of 1 dimensional figures, right? See, the edges are 1 dimensional, 1 dimensional, 1 dimensional. This is 2 dimensional. So that's why when you apply boundary over the boundary of k simplex, then boundary that we will get on that simplex will be of k minus 1, right? Because this is simplex, right? This del k sigma again become a simplex of k minus 1 dimension. So if I apply boundary on it, then del will have subscript k minus 1. Okay, let's take an example where I have del 2. So del 2 sigma of v0, v1 and v2 we have already computed above that it is v0 v1 v2 minus v0 v2 plus v0 v1, right? That's what we have computed here. So if I again apply boundary on it, so we know that it is of dimension 1, dimension 1, dimension 1. So let's apply boundary operator again on it. So del 1 of del 2 sigma will be del 1 of v1 v2 minus v0 v2 plus v0 v1. So you can expand it and it will look something like this: del 1 of v1 v2 minus del 1 of v0 v2 plus del 1 of v0 v1. So this will again become a 1 dimensional simplex, and how you will get v2 minus v1. I'm applying the definition that we have defined over here. It is a linear combination of their faces. So faces of v1 v2 will be v2 and v1. First face will be eliminate this v1 and we'll get v2, and eliminate v2 and we'll get v1. Similarly here, eliminate v0 we'll get v2, eliminate v2 we'll get v0. Again here v1 minus v0. If you see here, v2 get cancelled by v2, this v1 get cancelled by this v1, and this v0 is cancelled by this v0, and we are left with nothing but only the 0. We are left with 0. So this shows this property, this result: boundary of boundary is always 0. So in general, del k minus 1 of del k of any simplex sigma is always 0.